Good morning everyone. I hope that if you are watching this prior to the paper 2 chemistry A-level exam that's happening today, I hope that that goes incredibly well. If you're watching it after the exam has been, I hope that the exam went well. Love to hear how you got on in the comments, but of course now our attention turns to the paper 3 exam, which is on Friday. So today I am bringing you 2 multiple choice questions. And my plan for the next couple of days is to cover some practicals and some more multiple choice questions. And as always, any requests, please let me know. In these 2 multiple choice questions, we're having a look at redox and we're having a think about oxidation states and reducing agents in the first question. And in the second, we're having a think about equilibrium and how changing pressure and temperature affects the position of equilibrium and how we can then learn the colour of one of the 2 species that we have at equilibrium, and also the nature of the forward reaction in terms of is it X or endothermic. So I thought these were quite interesting questions, and I've chosen some other what I consider to be interesting multiple choice questions and a couple of practical ones as well. So let's get started with the first one. So don't worry about the fact that it's unbalanced. This came as like a 2-parter where one of the parts was to balance the redox equation. But I chose this one because when we've got an overall redox equation, we're perhaps a bit more limited. I wouldn't necessarily say harder, but we're a bit more limited in how we can figure out what is acting as the reducing agent in the reaction, or maybe the oxidizing agent in the reaction. So I guess one of the things that, if you've watched my videos before, I will always encourage is that when it says either oxidizing or reducing agent, that we have a think about what happens to the oxidizing or reducing agent itself. So a reducing agent has the ability to reduce something else, and it does that by itself being oxidized. So in order to give electrons to something else, it needs to be able to lose them. So that is the first thing that I would always do. And obviously I've been in this game for quite a while, is think about, right, reducing agents are themselves oxidized. And then we can have a think about what that means, because oxidation, there's a couple of definitions. And if we have a full sort of redox equation, it's not going to be the easiest way to have a think about oxidation in terms of loss of electrons. If you had half equations, that would be the easiest thing to do, hands down. But we don't have electrons here because it's not a half equation, it's an overall redox equation. So therefore, we want to be thinking about oxidation states, and an increase in oxidation state shows that oxidation is occurring, whereas a decrease in oxidation state shows reduction is occurring. So that's what we're going to be looking for in this equation. Where do we find that there has been an increase in oxidation state of an element? Now, in terms of the options that we're given, it might be that we can rule out one of those straight away, which would be the K+. Because potassium is a group 1 metal, group 1 metals always have a +1 oxidation state when they are a part of a compound. So that is physically impossible to be changed. So we can already rule that one out because it has a fixed oxidation state. And the other one that you might be thinking, oh, well, maybe we can rule that one out as well, is the H+. Now, again, I suppose what I needed to do for K+ as well is see whether it was turning into an element, because if it was an element, then it would have changed its oxidation state to 0, because all elements have oxidation states of 0. But if it's starting at +1 and going down to 0, that wouldn't be an increase in oxidation state, that would be a decrease in oxidation state. So even if it was forming an element, that wouldn't be what we'd be looking for. And so I guess the argument's the same here for H+. We've got H's in this H2C2O4, and we can see that the C2O4 2- ion is -2 for a charge, so the H will each be +1. In sulfuric acid, the H is a H+, so +1. In water, +1. So again, that's not changing either. Had it have become an element, then again, it would have been a decrease in oxidation state. So that also wouldn't have been what we were looking for here. Had the hydrogen have formed with the K, the potassium, if we have a metal hydride, so KH, because the potassium would need to have been +1, the H would have gone to being -1, and that's the exception for hydrogen, is in a metal hydride, the hydrogen will be -1, not +1. But again, we don't have one of those. So it's not going to be the H+, because that's going to stay fixed throughout the experiment. So not that one either. So that then leaves us with the C2O4 2-, so thinking about what might be happening to the carbon, and we can see that the product containing carbon is CO2, so we can have a think about the oxidation state of the carbon here and the carbon here and see what's going on there. And then our other option is the Cr2O7 2- ions, are thinking about the chromium, and the product containing the chromium is here. So because I've just mentioned that, let's do the chromium first. So we can either figure it out from the ion or from the compound, because the 2Ks are each +1. So that's going to give us +2, which then is where the -2 charge on this comes from. If we've got 7 oxygens, they're each -2. So that's -14 +2, which is -12. So the 2 chromiums have to equal +12. So the chromium initially is +6. And then in the product, we've got 2 chromiums bonded with 3 sulfate ions, and a sulfate ion is -2 overall. So we've got 3 lots of -2 for everything in that bracket, which takes me to -6. So the 2 chromiums have to be +6. So each chromium has to be +3. So here we're going from +6 to +3, which is a change in oxidation state, but it's not an increase. So this would be our oxidizing agent because it's self-reduced. So not that one, which means that, of course, we now have our answer, but let me just prove to you that it is the right answer. So again, we can either use the ion or the compound. Each H is +1, so that's going to take us to +2. Again, charge on the ion is -2. Each oxygen, -2, takes us to -8, +2, -6. So the 2 carbons have to be +6, so each will be +3. So we now need to have the oxidation state of carbon in the product higher than +3. And in CO2, each oxygen is -2 and there's 2 of them, -4, carbon has to be +4. Increase in oxidation state, oxidation, and if itself is oxidized, it's going to be able to act as our reducing agent. So that will be our answer there. If anyone has any questions about reducing agents, oxidizing agents, ways that we can figure out whether something has been oxidized or reduced, please, as always, don't hesitate to drop me a query in the comments or send me a direct message, okay? And then for the second question, we have got a pale brown mixture of NO2 and N2O4, which we've allowed to reach equilibrium in a sealed gas syringe, and we've been given the equation for that. So 2NO2 becoming N2O4. Then we've got some information about how we're going to influence the pressure and the temperature. So for the pressure, it says when the plunger is pushed further into the syringe, the pressure increases and the mixture becomes paler in colour. Now, even before I read anything else, what my gut instinct to do is to say if the pressure is increasing the pressure will always favour the side with fewer moles of gas. So when we increase the pressure, it's therefore going to favour the forwards reaction because there are fewer moles of gas on the product side. And if a mixture therefore becomes paler in colour, that tells us that the N2O4 has to be colourless. Because if increasing the pressure is making it become paler, the forwards reaction is what is being favoured when we increase the pressure, so that has to be true. Now, one of the things that we're figuring out in this question is whether the NO2 is brown or colourless. Well, we've just figured out that the N2O4 is colourless, so that means it can't be C and it can't be D based on the first piece of information we've got here. Now, in order to work out whether the forward reaction is exo or endothermic, to choose between options A or B, we need the second sentence, which annoyingly we can't really do a lot with until we've done the pressure part. So if you can't do the pressure part, a guess is what you would need to do here, but hopefully that makes sense. When the syringe is placed in a hot oven, the mixture becomes darker. So if we think about a hot oven, that is going to be increasing the temperature. And when we increase the temperature, that always favours the endothermic reaction. And the other key piece of information is that it becomes darker in colour. And we now know that the product, the N2O4, is colourless. So if it becomes darker in colour, it has to favour the backwards reaction, as the NO2 is the one that's brown. So therefore, increasing the temperature favours the backwards reaction, so the backwards reaction has to be endothermic. Therefore, the forward reaction has to be exothermic, because in any reversible reaction we have one of the two reactions being endothermic and the other being exo. So if we know backwards is endo, then we know that the forward reaction has to be exothermic. So we can therefore rule out option B, leaving us with A as our final answer. So just like with any sort of equilibria question, the key thing to know here is what increasing the pressure favours. So remember, Le Chatelier said that the system will always move to oppose the change that is imposed upon it. So if we're making the pressure higher, it's going to want to shift the position of equilibrium to where it can reduce that pressure again. And if there's fewer moles of gas, then we've got fewer collisions with the external walls of the container, and that will bring the pressure down. Similarly, if we make it warmer by increasing the temperature, it's going to want to bring that temperature back down by absorbing that additional heat, and that's why it's going to favour the endothermic reaction. So if we know what an increase in pressure favours, we know what an increase in temperature favours, we should be fine with all of our sort of equilibria questions. They are a bit tricky to word, but remember, which way is the position of equilibrium shifted, left or right? Why? What is being favoured by doing that? And then your final point should be in relation to the opposing of the change. Now, don't say to oppose the change, because that's not specific enough. It would be to oppose the increase in pressure or to oppose the increase in temperature. And there we have it. First two multiple choice questions done. Any specific requests, as I said at the start, just let me know. And I wish you all the very best with your revision this week, and obviously any and all exams that you have this week. I'll catch you guys soon. Take care of yourselves. Bye.